Welcome, pre-calculus students, to lesson 2.4 on division and zeros. I'll tell you, in this lesson, this is what mathematics really teaches you at a basic level, is staying organized. Structure and organization is key to a lot of mathematics, but I will tell you for this lesson, it's really, really key. So we're going to look back, some of you may remember long division from elementary school, and those skills are going to come into play with us in dividing polynomials, doing long division with polynomials. So over to the side here, we've got some just steps that we're going to follow as we do the division of polynomials. So what I want you to do is we're going to focus in on just the leading terms. Okay? So we're looking at the leading terms of these polynomials. So I'm going to be looking in on this x value. That's the leading term of that. And we're going to look at the leading term right here. Okay? So we're going to do the step by step. And what we're going to look at is we're going to divide these leading terms. So I'm looking at, well, how do I, what do I, if I take x to the third divided by x, or I like to think about it just the other way around. I'd like to think about what am I going to multiply x by to be x to the third? And the answer to that question is x squared. So we did that step. Move on to the next step. It says multiply the quotient in the divisor. Okay, so we're going to multiply this quotient, this x squared, by this divisor. So we're taking x squared and multiplying it by that x minus 2. Okay, and we're going to line that up underneath. So x squared times x is x to the third. X squared times minus 2 is a minus 2x. So we got that step done. And I'm sorry, it should be should be 2x squared there, my bad. X squared times minus 2 is minus 2x squared. So then we're going to subtract. And what I like to think about as I do this in the subtracting, it's really saying or add the opposites. So what I like to think about is I say change the signs, and then I can add these. So that will go away. When I add these together, I get 3x squared. And that process is done. And we're going to need to carry down the next terms. So we need to carry down the minus 5x and the minus 2. So that's done. And then we're just going to repeat. We're going to repeat this process. So I'll do it again, but now in a different color. Okay. So now what I'm looking at again is the leading terms. I'm looking at this x in this leading term of 3x squared. I'm thinking to myself, well, 3x squared divided by x, or you can think about x. What do I multiply x by to give me 3x squared? And that would be 3x. So did that part. Now I'm going to multiply that quotient, that 3x, times that x minus 2 up front. So I'm taking this 3x, the piece that we just got right there, times that divisor, that x minus 2. And when I do this here, I get 3x squared, and then 3x times minus 2 is a minus 6x. Okay, so I did that, and now we're going to do the subtraction. Or as I like to think about it, I say change the signs and add. Because when I put those together, that goes away. Bring that together, I just get x. So that's done. And now carry down the next term. And we're done there. So do it one more time here, the way it looks. I'm going to look at the leading term here, leading term there. X divided by x, or what do I multiply x by to give me x? It's just a positive 1. So we've got that done. Take this, the quotient here, the 1, times that divisor, so that 1 times x minus 2, and that just gives me x minus 2. So I do the multiplying. And then subtract, or as again, like I like to say, change the signs. We add them, goes away, and there's no remainder. So there's our answer. Right here. Oops. Is the x squared minus or plus 3x plus 1 is our answer when we divide. Now, there's another way to do this, and it's called synthetic division. We just did long division. So there is another way to do this called synthetic division, and we'll get that process written down. So again, what we're going to do is we're taking that original problem, which was the x to the third plus x squared minus 5x minus 2, and we're dividing that by x minus 2. Okay? So here's what we do, is we take, the first step is we write only the 0 of the divisor. Okay, so the 0, what makes this 0, and that's 2. So we write down only the 0 of the divisor, and then the coefficients of the dividend. All right, we kind of write those down a special way. You kind of box that in, and then the coefficients are 1, 1, negative 5, negative 2. So the next step here says to bring down the first coefficient. So we're just going to bring down this first coefficient. We're going to have a little line here. Bring down this first coefficient and just write it down. And then what we do is we multiply the 0 of the divisor. In other words, we take this 2 out here and multiply it times this 1. That's the first coefficient. And then we'll put that result right here. So again, we're taking this 2 times the 1 and putting it right there. Okay, and then we'll add these results here. So this is just 3. And then we'll do that again. We'll take this 2 times the 3 and put that result right there, which is 6. Add that up, I get 1. Do it again, take that 2 times the 1, gives me 2. Add that up, and I get a 0 over here. Now that 0 is at the end, so I like to box that in, because that's really our remainder. And if we look at our answer, we take this down by 1 here. So this is, when we were dividing this, we're going to be, you can't get that, to get that x to be x squared, it has to be, or x cubed, it has to be an x squared. So this is really the term on that x squared. This one here is the term on the x. This one is the constant. And there's our answer. Now, we wouldn't necessarily need to have that 1 written there. So you could just write it as x squared plus 3x plus 1. And as you noticed, that's the same answer that we had up here. So different process, same answer. I think a lot of people really like the synthetic division. So let's continue. Let's look at doing some exercise, some problems together here before we turn you loose. So we're doing long division. Okay. So let's just start off with the problem. So this is this top part divided by the bottom part. So if we want to look at how to write this out, we're going to take the top part divided by the bottom part. So it's this top part, 2x to the 4th plus x to the 3rd. And here's a little trick, a little tip I should tell you, is that make sure to represent each of the different terms. Now you notice there's no squared term or there's no x term, but you got to represent it inside the division here. So we're going to go with that as a plus 0x squared, because there aren't any x squareds. There aren't any x's. And then we have the minus 3. So you need those placeholders. You absolutely need those placeholders of doing this problem. And again, that's divided by this x squared plus x plus 1. So you start off by looking at those leading terms and looking at, well, what do I multiply x squared by to give me 2x to the fourth? And that'd be 2x squared. So I'm going to line it up above the x squared here. So I'm going to put 2x squared there. And we take this term here and multiply it times all these pieces here. So again, we're taking that 2x squared times x squared plus x plus 1 to give me that next row of numbers. So if I distribute this, I get 2x to the fourth. 2x squared times x is 2x to the third. And then 2x squared times 1 is just 2x squared. So you can see now that's why we have that placeholder there, so they can line up. And then there's the change the signs piece. Add these together, that goes away. Add these together, that's a negative x to the third. This would be a negative 2x squared. And then bring down the other pieces. So you get 0x minus 3. Okay. Now we look at, what do I multiply this by? The x squared to give me that negative x to the third. And that'd just be a negative x. So then we do negative x times the x squared plus x plus 1. And again, if we distribute that, it would be negative x to the third, and then negative x squared, and then negative x. And then change the signs, and we can add. It goes away. This would be negative 2x squared and negative x would give me negative 3x squared. Or I'm sorry, that's a plus, my bad. It's a plus. So that would actually be negative 2x squared plus x would be negative x squared. Look a little sloppy there, that's why. Adding that together, that's just plus x, and then bring down the last, which is minus 3. So then looking at what do I multiply this by to give me this, and that's just a negative 1. And then we take negative 1 times this divisor and distribute that all out. That'd be negative x squared, negative x, negative 1. And then remember to change the signs. We're adding, so that goes away. X and negative 1x. Or wait, I'm sorry, again, that's a plus sign. Those didn't really work too well there. So that would actually be a 2x. And then negative 3 and 1 is negative 2. Now we can't do this anymore. This actually is our remainder. So how do we write that? Let's see if you remember from way back when you did long division the first time and you end up with the remainders. What you do is, here's our answer up there. It's still this 2x squared minus x minus 1. And then in the past, you may have written like remainder, and then this could say 2x minus 2. So you wrote like remainder what that is. Well, we do a little bit better than that. What we do is we're going to write that as a fraction piece. So I'm going to say this is plus this amount here. This is the 2x minus 2 out of our divisor. So our x squared plus x plus 1. So that's kind of how we officially write this problem. Okay. Well, let's give you a chance at it. Have you tried that one on your own? Pause the video, come back, and see if you got it right. All right, and hopefully this is what you came up with. Double check your answers. You came up with a 3x squared minus 6x minus 4. And the remainder is minus 2, so we take that minus 2 over our divisor. Okay, pause it if you need to take a little bit longer look at it. But let's move on and practice a synthetic division problem, and then have you do one as well. So this first one here, synthetic division. Now, there is a little trick here, and it's kind of being a little nasty here. Actually, with this one, you can't do it. Okay, you can't do synthetic division when your divisor is nonlinear. Okay. And this is a nonlinear. That was obviously a parabola. That's some type of parabola that makes there. So that's the problem with synthetic division. You can't do it when your divisor is nonlinear. Linear means it has to be, a power. The degree of the divisor has to be 1. Okay, so kind of tricked you there. Can't do this one with synthetic division. So if you use synthetic division, just couldn't do it. You'd have to go and do this with long division. Okay, so we won't have a independent practice for you here. We just have another guided one, because here, this one I can. Okay, I do have my divisor is a degree of 1, so I can do the synthetic division. So what we're going to look at is this piece right here. That's our divisor, and we got to look at what's the 0 of that. So again, you can set that equal to 0 and say, well, okay, x equals -2. That's going to be the piece in the little box right here. We then have to look at the top and look at all the coefficients. Now remember to add the placeholders there. So this is 3x to the third. There is no 0 term, or x squared term, so we go 0x squared. And it's -16x, and then -10. So we can see 3, 2, 1, nothing. So if I pull down those coefficients, the first one is 3, next one is 0, next one is -16, next one is -10. So we'll draw the line, just bring down the first one, and then we just multiply. -2 times 3 is -6. And we just add those. That gives me -6. -2 times -6 is a +12. Add those, gives me -4. -2 times -4 is a +8. And we've got -2. So I'm going to kind of box that last one there, because that's going to be, this piece here is going to be my remainder. Oops, sorry, that's sloppy writing there. So our final answer here is 3. And again, we're going to go one less because we're taking this x into the x to the third, or x to the third divided by x. So it would end up with x squared minus 6x minus 4. And then here's my remainder. So we'd go -2 out of our divisor, which is x plus 2. All right, then let's move on to another topic here. Okay, and this isn't moving. There we go. Sorry about that. So we're going to look at the remainder theorem and the factor theorem. Okay, so we'll see kind of how we're going to use these and play these out here. The remainder theorem says that if a polynomial, some p of x, okay, so here's a p of x right here. Okay, so if a polynomial is divided by x minus c, so that's what we're going to look at here. We're going to look at this polynomial. So we're going to write this over here. You've got this x to the third plus 2x squared minus 5x minus 6 is divided by, so if some polynomial is divided by x minus c. Excuse me. So what we're going to do is we're looking to see if this is a factor. So in other words, if I took this x minus 2, so if a polynomial p of x is divided by some x minus c, well, they're telling me then that the remainder, so when we divide this all out, what we get for a remainder is really just doing p of c. So we're going to look at finding out what is p of c. Okay. So in this case, x minus 2, our c value is 2. So you can see x minus c, it's x minus whatever that c value is. This is just my c value. So that's what I'm going to do, is I'm going to find out what p of 2 is. So when I put this in, I'm just substituting 2 into this equation. That's where I get the 2, that goes into the x, this is going into that x, that's going to that x. And do all the work here, I'll see that it comes up to be 0. Well, that's my remainder. My remainder is 0. Well, if my remainder is 0, then this factors into it. This x minus 2 factors perfectly into that polynomial. This will go in exactly. There will be no remainder. And that's what the factor theorem says, is that for a polynomial, p of x, okay, that this x minus c, this x minus 2 is a factor if and only if the p of c equals 0. So if this p of c equals 0. Well, we can double check this too, just to make sure, and we can do longer synthetic division. I'm assuming most people probably will do synthetic division, and we'll get this c value here. We'll get that c value, that's 2. And then again, bring down your coefficients, 1, 2, -5, -6. Bring down that first one, multiply, add, multiply, add, multiply, and add. See, that remainder is 0. So what I do know now, then, is that this answer, this is x squared plus 4x plus 3. This too is a factor, because I would know that x minus 2 times x squared plus 4x plus 3 will give me this answer. So that's kind of going on this next step here, is this writing it in factored form. So we're going to take this p of x that we had right up here and then write that in factored form. Well, we've almost got it totally factored here. So we've right now got p of x equals x minus 2 times this x squared plus 4x plus 3. We just need to continue factoring that piece so we can have it completely factored. So p of x equals, you can see why we had this as prerequisite material, because we're doing a lot of factoring. This is why we did that right at the beginning of the school year. So this trinomials break down into 2 binomials, and 2 numbers and multiplied give me 3, but when I add it give me 4. So let's say x plus 3 and x plus 1. So now I've got it completely factored. Well, that's nice. I love factored form because it's really easy to find the zeros then. Because all you do is you just set each of these pieces. You're saying 0 equals this x minus 2, x plus 3, x plus 1. And you're basically just setting each of these factors equal to 0, because you're saying, well, this times this times this equals 0. Well, one of these, either the x minus 2 equals 0, or the x plus 3 equals 0, or the x plus 1 equals 0, which is just x equals 2, x equals -3, or x equals -1. Those are the zeros. The next piece here is to find that y-intercept. Well, and that's where we know if we find that y-intercept of p of x equals that factor form of x minus 2, x plus 3, and x plus 1. To find the x-intercept, well, the x-intercept occurs when the x is 0. So we're really finding p of 0. So 0 minus 2 times 0 plus 3 times 0 plus 1. Well, this is -2, this is 3, and that's 1. And if you multiply that all out, it's -6. So our y-intercept is at 0, that's our x value that we put in, and -6. So all these pieces allow me to graph this, this function using everything that I know from earlier. And when I look at the original problem of p of x right here, equaling x to the third plus 2x squared minus 5x minus 6. And if I wanted to graph that, okay, so we got to go back and think about all the things we just learned in section 2.3 as well too. I know this is an odd function because the highest degree is 3. Okay, so I have some general idea that this is odd. The leading coefficient is positive, so it's probably doing something like that in general. We're going to get a little more specific then with graphing the zeros to help us, and also the y-intercept. So if I'm going to graph that, let's just go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So I know there's zeros at 2, at -3, and -1. And again, because of what I know earlier up here, because it's an odd function and it's positive, it's got to start down here and kind of end up, that's that positive piece, but it's going like that. So I'm going to start down here, and it's going to go up until it hits that point. Now we'll talk about that in a second here too. But we're also getting another point down here too is the y-intercept. So 1, 2, 3, 4, 5, 6. I know there's the y-intercept. So this also goes back to the multiplicity pieces. And if I look back here on my different zeros, these all just had multiplicities of 1 because the degree in each of those factors is 1. 1 is an odd number, so multiplicity, an odd multiplicity means it passes through. So these all of these pass through. None of them bounce. There is no even power on the factors. So again, we'll start down here, and we'll go up and down until we come back down, hit the y-intercept, and then back up through their point. And that's generally what our graph should look like. Okay? All right, then we move on to our last section in this section 2.4, last concept, called the rational zeros theorem. It says, if you are not given a zero, okay, so in other words, like back up here, we were found that we were given this x minus 2 as a factor. So knowing that 2 would be a 0, we could find the other pieces. Well, what if you are not given a 0? How do you go about figuring out what numbers to test? I'm going to test. We can narrow it down from all the infinite possibilities down to a few examples that we can test to see if there are zeros. And it's called the rational zeros theorem. And basically, if you read through all this, what we're going to do is we're going to look at the ratio of p divided by q. But what the heck is the p and the q? So the p value, where we get that from, it's the constant coefficient. It's the constant coefficient. So that's the one without a variable. So if I go back up to this previous problem, our constant coefficient here would be -6. The q is an integer factor of the leading coefficient. So we are looking at the leading coefficient. In this problem up here, our q would have been the leading coefficient here, which is 1. So we take the ratio of the p over the q, the -6 over the 1, and test that as a factor. Okay, so we have to look at all the different factors of -6. Okay, so you look at -6 and 1, -2 and 3, -3 and 2, -1 and 6. We'll do that. I'll show that in an example here on the next page with the problem. So you got to look at all the different factors, because this one, the problem we would have done would have been -6. You look at all the factors of that. So let me just get into a problem here and kind of show you how that all works out. Okay. So here's our polynomial. All right. So if I look at this, I'm just going to blow this up for you so I get a little bit better writing room here too. What I want to do is look at finding where my p's and my q's are. Okay, so looking at first of all, this finding all the p's. Remember now, the p's all come from your constant coefficient. That's my p's. Okay, so I'm looking at trying to find all the factors of 8. Okay, because those are all the p's. So what I've got, all the numbers that go into 8. There's a plus or a minus 1 that goes into 8. Plus or minus 2 goes into 8. Plus or minus 4 goes into 8. And also a plus or a minus 8 goes into 8. Then I got to look at all the q's. Well, the leading coefficient here is 2. Okay, so I'm going to look at all the factors of 2. Well, all the factors of 2 are plus or minus 1 and plus or minus 2. So what I need to do is I need to look to narrow down to all the possible zeros for this function. I'm going to list all the possible p's over q's. And this can get kind of long. So that's where it's going to be very important to be organized. So I'm going to take this p and look at dividing it by this q, and look at dividing it by this q. So plus or minus 1 divided by plus or minus 1 is plus or minus 1. Plus or minus 1 divided by plus or minus 2 would be plus or minus 1/2. And then I'm going to repeat that with the other examples here as well. So I'm going to take this 2 and divide it by this p divided by these q's. So plus or minus 2 divided by plus or minus 1 is plus or minus 2. And then plus or minus 2 divided by plus or minus 2 is plus or minus 1. And we've already got that, so I don't need to write it down again. Then we'll take this p and divide it by each of its q's. So plus or minus 4 divided by plus or minus 1 is plus or minus 4. Plus or minus 4 divided by plus or minus 2 is plus or minus 2. And again, I've already got that. So sometimes they repeat, and you don't have to write them down the extra ones. And the last thing, we'll take this p and divide it by these q's. So plus or minus 8 divided by plus or minus 1 is plus or minus 8. Plus or minus 8 divided by plus or minus 2 is plus or minus 4, so I've already got that. So what I've got here right now, these are all possible zeros for this function. All right. So what we're going to do now is test those zeros using the remainder theorem. Okay, so I'm going to look at taking each of these, taking f of whatever each of these are, each of those p's over q's, and finding out which ones make it 0. So in other words, I got to put in each of these problems, I'm going to put 1 in to this equation, put 1 in there, 1 in there, 1 in there, 1 in there, and see if I get 0. Okay, so I'm looking at, doing is p, if this is, I should use this as f of x. If f of x, because this is what I was using up here, was an f. So f of x equals 2x to the 4th minus 7x to the 3rd minus 8x squared plus 14x plus 8. So in other words, taking that equation that's from over here, and I'm going to test each of these. So I got to go and find f of 1. So I'm going to take that positive 1 and find out what that answer is. And then do f of negative 1, find out what that answer is. F of 1/2, find out what that answer is. F of negative 1/2, find out what that answer is. F of 2, F of negative 2, and then find F of 4, F of negative 4, and then F of 8, and F of negative 8. So find out which one of these comes out to be 0? Well, what we can do with this problem is kind of help narrow some of these answers down. And that's how we can do this, by using a calculator. Okay, so I can show you that here in just a second too. So it can be a little tedious work to put this in, and that's what I was going to say with the calculator. What you can do is if you go to Desmos, what you can see is when you graph this that there are 4 zeros, which makes sense because the degree of this polynomial is 4. The most it would have would be 4. But we're only looking for the rational zeros. So we look at the solutions. Here's one at 4. Here's one that's like a little short of 1.5. Here's one that's at a -0.5. This one's a little, it's maybe like -1 and almost 3/4. So out of all the numbers we have on the list, the ones that are going to work for us are going to be the ones at 4. So that gives me a 0, and the one that was at -1/2. The other ones we have here they didn't have zeros there. They didn't cross the x-axis at any of these other points. So what we have is we have 2 rational roots. All right. The other 2 would either be irrational or imaginary. Okay, so you notice there were 4 there. So the other 2 are, in that case, would be irrational. Imaginary, you wouldn't have those graphed. So that's what we found is we've got two zeros, that x equals either -1/2 or x equals 4 as our possible, or as rational zeros. So using that information, we can use synthetic division to help us find the other zeros in our problem. So in doing that, what we can do is double check this here. We know that 4 is a 0, so then I know that x minus 4 should go into our function of 2x to the 4th minus 7x to the 3rd minus 8x squared plus 14x plus 8. So when we do the synthetic division, I would take this 4, box it in, and then take each of the coefficients, 2, -7, -8, 14, and 8, and perform the synthetic division. So bring that down, multiply and add, multiply and add, multiply and add, multiply and add. So that's where we get that remainder of 0. So far then, what we have in factoring this problem is we would have for our function in factored form, f of x equals this x minus 4, and then our polynomial that we create from here, which should be 2x, and again down 1 from there, so we add to the 3rd, plus x squared minus 4x minus 2. So then what we're going to do is take this part right here. And I know from above here that x minus 1/2 was another factor. So what I can do then is take that x, again, knowing that that's a factor, that x minus 1/2, I can take this -1/2, box that in, and factor it into this piece to see if I can break that down for another factor. So I'll bring down the coefficients. So that's 2, 1, -4, -2. All right. And we can draw the line and bring the first one down. And then go ahead and do the multiplying and adding. Multiply here would be -1. So if I add that, that's 0. -1/2 times 0 is 0. And then add that. -1/2 times a -4 is a +2. And see, again, we get a remainder of 0. So that again proves that that's a factor of that. So now what I've got is I've got f of x equals, I've got that first factor of x minus 4. And I've got this x minus the -1/2, which would be +1/2. And I've got this stuff remaining here. So again, going one less in the powers from here. So that's 2x squared. There is no x term. And then -4. Okay. So let's continue to do some more factoring then. Because I look here, I should be able to get a GCF out of that. So we got x minus 4, we got x plus 1/2. I would have to take a 2 out of that, and I'd be left with x squared minus 2. And we can also factor this piece here well, I guess that's, no, I guess we really can't factor that. It's not I thought for a second there was a difference of perfect squares, but it's not. So I can't really factor that. If I'm looking for all the other factors, I know this here, if I set these pieces all equal to 0, I know x minus 4 equals 0, so that gives me a 0 of 4. Set this x plus 1/2 equal to 0. X equals -1/2 is one of the factors. 2, I don't worry about. I don't set that equal to 0. But if I set this x squared minus 2 equal to 0, I get x squared equals 2. Square root both sides, and I get x. Oops, get a little room here. I get x equals plus or minus the square root of 2. These are the irrational roots. So that's all 4 of the roots I have is 4, -1/2. And remember from that graph, there was those other ones that weren't right quite on the line. So it was just that negative root 2 and positive root 2. All right, a lot of work there, a lot of work. So really what we can do here is run through one more example, and I'll help you kind of see the process again. So the idea is that we want to be able to factor these polynomials completely by using the rational roots theorem. Okay, so if I'm going to use that rational roots theorem, first thing I'm going to do is I'm going to list all of my p's. So again, my p's all come from that coefficient or that constant coefficient. And then I'm going to list all the q's, and that comes from my leading term coefficient. So, I like to just go ahead and start listing those. P, so if I'm looking at all the factors that go into 51, well, plus or minus 1 go into 51, as well as plus or minus 51. 1 times 51 is 51. Now you got to think about what other numbers multiply give me 51. Well, I know 3 does. Plus or minus 3 times plus or minus 17 gives me 51. And those are all the factors of 51. Let's look at Q. Look at 5. All the factors of 5. Plus or minus 1 and plus or minus 5. And I believe that would be it. So what I'm going to do is I'm going to now list all of the P's over the Q's. All right, so I'm going to start with this one. Plus or minus 1 over plus or minus 1 is plus or minus 1. Plus or minus 1 over the plus or minus 5 is plus or minus 1/5. And just continue now, go to the next one. 51 over 1, so plus or minus 51. And then here, plus or minus 51 over 5. And so that was these. Now I'll take the 3. Plus or minus 3 over 1 is plus or minus 3. Plus or minus 3 over plus or minus 5 is plus or minus 3/5. So the last one is just a 17, so plus or minus 17, and then plus or minus 17 over 5. So those are all of the possible rational roots. Okay? So what you got to do is, again, now you're going to take this f of x equals 5x to the third minus 7x squared minus 49x plus 51. And you're going to find, start with f of 1, then f of negative 1, etc. Try each and every one. You got 2, 4, 6, 8, 10, 12, 14, 16 different options that you got to find out which one of those, when I plug that number in, gives me 0, because then I will know that that is a rational 0, that will have a factor that in there. So, all right, so just kind of cut to the chase a little bit. I will tell you that f of 1 does work. If I put 1 into this, I do get 0. I'm going to check here. This would be 5 minus 7, which would be negative 2. Negative 2 and negative 49 is negative 51, and then 51 and negative 51 is 0. So that one works. So, and you can even test it by saying that taking this 1 and doing the synthetic division into this. So we get 5, negative 7. We'd have to put a 0 in there. I'm sorry, we wouldn't have to put a 0 in there. There's a 49 there. So my bad. Because it does go 3, 2, 1, 0. So you get 5, negative 7, negative 49, and 51. And if we bring the first one down, multiply and add, multiply and add, multiply and add. That gives me 0, so you can see that it does work. So what I do know is that 1 is a 0, so that makes x minus 1 a factor. And here would be what my quotient would be. So again, 1 less than the starting value, so this would be 5x squared minus 2x minus 5. And then it's just factoring that piece. So you got x minus 1, and that should factor into 2 binomials. And using our factoring skills, we can look at this and say, well, no, this has got to be 5x, this has got to be an x, and let's see, this would be minus 17 and a positive 3, because then 5x times 3x here, and the outside is 15x, the inside is minus 17x, that gives me the negative 2, and then the last negative 17 and 3 gives me negative 51. So those are all factors. If I want to find all the zeros, you can set these all equal to 0. So x equals 1, which we knew already. This one, 5x minus 17 equals 0. So this would be 5x equals 17. X equals 17 fifths. Okay, so there we see that that would have been one of the other rational roots. And then here, the x plus 3 equals 0, or x equals negative 3 is another one too. So the negative 3 in there would have worked as well. So, and that's the most zeros it could have, because that degree of the polynomial is 3, so that tells you there's a maximum of 3 roots, and that all happen to be rational numbers. Okay. All right, last little problem here. We'll do it one more time. Just kind of look at all the different pieces put together. So first thing this says, we want to find all the zeros using the rational zero theorem. Okay. So again, what we're going to look for, we've got the p's right here, we've got the q's right there. So we want to list all those possible roots, all those possible, we should say, rational roots of this polynomial. So So we're going to look at all of the p's over the q's. So we're going to first of all look at just looking at all the factors of p. So p, all the factors of 15. So plus or minus 1, plus or minus 15, because 1 times 15 is 15, plus or minus 3, and plus or minus 5. Those are all the p's that we could get. For q, for 2, the only factors are plus or minus 1 and plus or minus 2. So now we're going to look at all the p's over the q's. So we'll start with this one and take it over those. So we have plus or minus 1 and then plus or minus a half. Okay. Take the next one, plus or minus 15 over 1, which is just 15, plus or minus 15 over plus or minus 2. So it doesn't work out evenly, so this way is plus or minus 15 over 2. And take this one over each of those, plus or minus 3, plus or minus 3 halves. And then 5, plus or minus 5, and plus or minus 5 halves. Those are all the possible rational roots of this polynomial. This problem then just asks us to check by synthetic division to see if 1 or negative 1, to see if those are roots. Okay, well, let's take them one at a time. We'll take the 1 and do this by synthetic division. So looking at all the coefficients, we'll do 2, negative 9, 4, and 15. Bring down the first one, multiply and add, multiply and add, multiply, and, whoops, I made a mistake here. This was 1 times negative 7. No, I'm good. Just a little mistake. Sorry. Well, and this would be negative 3. So this would be 12. That's my remainder. I don't want a remainder if I want it to be a factor. Okay? So 1 is not a root. We can try negative 1. And we have 2, negative 9, 4, and 15. Draw the line, bring down the first one, multiply, which gives me negative 2, and add, so it gives me negative 11. Multiply here, gives me positive 11, add, it's 15, multiply, and add, gives me 0. That's good. I like that. I want that remainder of 0, because that will tell me then that negative 1 is a root. All right? So I know negative 1 is a root. And it says, what is the polynomial that is obtained after division? Okay, well, there we can use that there, and that would be the 2x squared minus 11x plus 15. That'd be the polynomial that's left. If I factor that, then that factors into 2 polynomials. I know I have a 2x here and an x here, and then I got to split up that 15. So let's see, it's negative, so I got to have 2 negatives, so maybe like negative 5 and negative 3. So when I do the outsides, I get negative 6x, insides negative 5x, it does give me that negative 11x. So there's my polynomial factored. Set each of these factors equal to 0. So I will take this 2x minus 5, set that equal to 0. And take this x minus 3 and set that equal to 0. So I get 2x equals 5, or x equals 5 halves. Here, x equals 3. So the other 2 roots are 5 halves and 3. Those are the other 2 roots besides our negative 1. Those are our 3 roots for this problem. So it says, were these roots in the list of possible roots? Well, let's go back up and look. There was negative 1 in there. Yep. Was the 5 halves in there? Yep. Was there? And was the 3 in there? Yep. Let's put that one right there. So, yes. How many roots should this polynomial have? Well, again, if you remember here, the polynomial at the beginning here has a degree of 3, so the maximum it should have is 3, because, again, it's a degree of 3. What is the y-intercept? Well, if I want to find out what the y-intercept is, I've got to put x equals 0 into this this function. Okay, so I'm finding f of 0 of that function. So I'm going to jump back and forth here. So that's f of 0 of that 2x to the third. I don't know what this was. Minus 9x squared. Plus 4x plus 15. So I'm just putting zeros in for that. So put 2 times 0 to the third minus 9 times 0 squared plus 4 times 0 plus 15. And those are all zeros. So this should just equal 15. The y-intercept is at 0, 15. So if I'm going to, probably would have said maybe graph this polynomial first so we could then look at the end behavior. But in general, we can look at that end behavior first. Again, this is a third degree polynomial with a positive coefficient in front. So I know in general that this graph, is doing something like this. Okay. So if I look at that end behavior as x goes to negative infinity, so the limit as x goes to negative infinity would equal negative infinity because it's going down. Here the limit, oops, I should have had f of x there. The limit of this function as x goes to positive infinity, so as x goes this way, the graph's going up, so that's going to positive infinity. To finally graph this, again, knowing that the roots are -1, so if I go -1, 5 halves, which is 2.5, so 1, 2, 3, so 5 halves, and also 3, the y-intercept is at 0, 15, so let's go 5, 10, 15. It generally has this pattern starting in the lower left corner. It's going to come up, hit up here, come back down, and go through and come back up and through here. Because again, these are all multiplicities of 1 from up above. Wow, that's a lot of stuff. A lot of problems. That's why this video was so long. So take a look at it, pause it, do where you need to look at some reviewing, and we'll take a couple days to work on some of these practice problems. And make sure you practice, make sure you ask your questions, and we'll get them answered. Thank you for sticking with me, everybody, and we'll see you in class.